So we're just going to do some problems in this video. Okay, before we start the problems, you can see 30 problems on this page. Before we do that, we're going to be just needing to come up with the areas. We need to determine the areas of each of these significant regions on this graph here. So this is the graph of f of x, as you can see here. You've got straight line segments, and then you've got a semicircle here. So let's start on the left-hand side. What's the area of this triangle? The area of the triangle is half of the base times the height. So you can see this region here has an area of 1. So the area right here is just 1/2. Okay, so the area is 1/2, and then the area of this region right here, kind of tricky here, but if we break it down into a few parts, we could see the area of this triangle. I should do this part here. The area of this triangle here, the tall, skinny one, it's half of the base times the height. So 1, 2, 3, 4, 5, 6. If you just count the square units of the rectangle, then you can cut that in half. So the area of that triangle without too much effort is 3. This is really helpful to do this, by the way, when you're doing these definite integral problems. And then this triangle area up here, 2, 4, 6, 8 is the area of the 2x4 rectangle, so half of 8 is 4. Okay, and then 1, 2, 3, 4 for this area here. We could have used the trapezoidal area of a trapezoid and found it that way. No need to here, but we've got these two here. This would be an area of 2, and then 1, 2, 3, 4. So this next triangular region here, we have 2 by 2 square, and half of the square is 2. The area of the half of the square. The area of the square is 4. Area of the triangle is 2. And then, just in case, let's find the area. Let's see. Either way, we're going to get fractions here. So I was going to say, what's the area of this entire triangle? Let's break it down into two little triangles. So the area of this little triangle here is 1/2, 1/2 again, and then the area of this triangle here is 1, 2. That's just 1. Okay, and then we have finally this semicircle. Well, we know that the area of a circle is pi r squared. The area, if this were an entire circle, we can see the radius is 2. And so the area of the circle, if we completed the circle, would be 4 pi, but the area of the semicircle then would be half of that area of the entire circle, so we get 2 pi. Okay, so now we have everything we need, and it may be helpful to write down the units here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then -1, -2, -3, and -4. Okay? So, we're ready to go. Problem number 1. You notice here I've got some problems in yellow and some in pink. Well, the yellow ones I'm going to do, and then the pink ones I'm going to ask you to pause the video and do them on your own. So, first one, we want to find the integral from 4 to 4 of f of t dt. In other words, we're integrating from 4 all the way to 4. Which, if you remember what we talked about in the last video, we know that when the upper and lower limits of integration are the same, then we don't have any area, so the area is 0. Okay. Well, again, reading these integral problems is just going to take a little getting used to. And we read this as the integral from 0 to 1 of f of t dt. Okay. Now, notice that this is the graph of f of x. This guy right here, should point this out. This is called a dummy variable. Okay, it doesn't matter what we use there. We could write f of b db, f of c dc. Typical would be f of x dx, but it really doesn't matter. It just represents the input. Okay, f is the rule, and f is the graph that you see here. F depends on x in the graph. F depends on t here. It doesn't really matter what that is. So the dummy variable being t, it could be an x dx, and it really should be for this to probably make more sense to you, but after you do a few of these, it shouldn't bother you at all, and if it does, then get over it. Well, no, just try to get used to it. It doesn't really matter. Replace it with an x if you want. Sorry, being a smart aleck and no one's here. All right, so the integral from 0 to 1 is just the area between the curve and the x-axis between 0 and 1. And we already determined that that area is equal to 2. Okay, that area is 2 because it's the area of that region right there. And then the area from 1 to 3, we can see that we just are integrating from 1 to 3, and we see that that area is 2 as well. Okay, so far so good. Area from 0 to 3. Well, if we integrate from 0 to 3, we accumulate all this area from 0 to 3. Integrating means we're accumulating. We're accumulating the area from 0 to 3, and so therefore we get 2 plus 2, which we know is 4. And then we go from 3 to 6. Now here's where we finally have to really start thinking if this is like, okay, this is really easy, Mr. Hawks, but from 3 to 6 now, okay, remember what we talked about. As long as the function is above the x-axis, when you integrate, you're getting the same as area. Well, if you integrate from 3 to 6, and you can see that the area of the region is 1 1/2, which is 3 halves. But when you integrate and the region is entirely below the x-axis, then we actually get negative 3 halves. So it's still the same area, but it's below the x-axis, and we indicate that. Just like velocity being negative means you're going to the left, or backwards or down. Well, integral of negative 3 halves means that all or most of the function f of x is below the x-axis on that interval. Okay? In this case, all of the function f of x lies below the x-axis on the interval from 3 to 6. Okay? Now here's the cool thing. If you really wanted to express the area in terms of a positive number, we know that we can flip the limits of integration around. We can integrate from 6 to 3, and integrating from 6 to 3 gives us actually a positive area. That's an equal sign, equals a positive 3 halves. Okay, so when you integrate from right to left, and the function is entirely below the x-axis, then you're going to get a positive number. All right, try the next couple on your own. Try number 7 and 8. Pause the video. I'm just going to keep going. The integral from 0 to 6 would be 4 minus 3 halves, and 8 halves minus 3 halves would be 5 halves. Okay. Integral from 6 to 10, well, that's just the area of that region, 2 pi. Okay. I'll do number 10. We went from 0 to 6, and we got 5 halves. And then we went from 6 to 10 and we got 2 pi. So we're just going to leave it like that. 5 halves plus 2 pi. Okay. Oop, sorry. Didn't realize you couldn't see that. So number 10 again is from 0 to 10. Number 10 is from 0 to 10. And that's 5 halves. So 0 to 6 would be 5 halves. We did that already. 4 minus 3 halves is 5 halves. And then we add to that the 2 pi. Okay. And then number 11, pause the video and do this one on your own. I'm going to keep going. We already just saw that from 0 to 10 is 5 halves plus 2 pi. So from 10 to 0 would be the opposite of that. If you distribute the minus sign, great job. If not, great job. All right, number 15, I'm going to do negative 4 to negative 3. Okay, so negative 4 to negative 3, I'm looking over here, and if I notice here, I've got an area of 1/2, and negative 4 to negative 3 means I'm integrating left to right, so I would get a negative 1/2 because the graph is entirely below the x-axis on that interval. Okay, now I didn't set you up very well for doing number 17, but I'm going to ask you to do that anyway. Okay, pause the video. Negative 4 to 10. If I go from negative 4 to 0, I already know, let's see, where could I do that? Use a different pen here. And if I go from, where can I do this work? There's no room. So negative 4 to 0. I just have to figure that out first. That's a negative 1/2 plus, what's all that area? 8 plus 3 is 11. So 22 halves minus 1/2 is 21/2. So integral is equal to negative 1/2 plus. So that's equal to 21/2. Okay. Well, from negative 4 then all the way to 10 would be 21/2 plus the 5/2 plus the integral from 0 to 10 plus the 2 pi. Okay. So that gives me that. And then, so yeah, 26/2, so 13 plus 2 pi. 13 plus 2 pi. All right. And then 0 to 10. All right, so here's what we're going to do. Going from 0 to 10 on number 19. So now you can't see the graph while I'm doing this. But what I will do is I'll flip back up here, and we want the absolute value of f of t, right? So if we want the absolute value of f of t, then I'll draw another graph, and let's see, what color have I not used yet? I haven't used blue. So in blue, I'm going to go ahead and draw the graph of the absolute value of f of x. Okay, so that's that part. So anything that falls below the x-axis on f of x is then reflected about the x-axis for the graph of the absolute value. If you think about it, what's the absolute value of negative 1? It's 1. What's the absolute value of negative 1/2? It's 1/2. So all of these points along the curve right down here where f of x is negative get reflected or get mapped onto the positive side of the x-axis. Okay, and then we just cruise along here until we see some more part of the graph underneath the x-axis, and we just draw its reflection. We did this when we converted velocity to speed. Okay, and then we have we can write down the area under the curve there, and the area under the curve here is 1/2. Over here it's 3/2. And so if we wanted to integrate from 0 to 10, all of this area, we just 4 plus 3/2 plus 2 pi. Okay, so we have 4 plus 3/2 plus 2 pi. That's the area under the curve of the absolute value of f of x, or f of t if you will. Okay, now how does that differ from this guy right here? Well, you're going to do number 20 on your own, and you're going to pause the video, you're going to come back. Okay, so sometimes this could be confusing, and you just have to be careful here. The absolute value of something is what you're going to be writing here. Okay, well, guess what? That something that you're trying to find the absolute value of is right here, 13 plus 2 pi. And so the absolute value of 13 plus 2 pi is 13 plus 2 pi. Okay, simple as that. Nice. All right. So I'm going to do number 23, and oh, these are kind of tricky. I don't know if I have enough room to do my work here. I'm going to do this in the next video.